Alright, so today we are going to be looking at 7.6 exponential growth. I've decided not to do exponential decay because the only examples that I can think of, or the ones we mainly go over, is half-life, which if you take grade 11 physics, I'll teach you all about half-life. But for the purpose of this course and the amount of time we have, I'm going to go over exponential growth because that's very important when, say, calculating compound interest when you're looking at finances, which is what our next unit actually is. So let's go over exponential growth, and then tomorrow, I will be posting a Google form quiz for chapter 7. And I'll let you have a couple of days to work on that, and probably Thursday and Friday I'll put up lessons for finances. So please go on to the Google Classroom and print the package for chapter 8, which is going to be our last chapter. I'm hoping to finish that by the end of next week. Okay, and then we'll have one last Google form quiz. And after that, I'll get back to you. Okay? Okay. So, let's look at this one, exponential growth. So because we're talking about growth, we are going to look at an exponential graph that looks like this. So the one that looks like this is our example where we would have a function with a base to an exponent, where our base is going to be greater than 1. That's when you get that growth. Otherwise you get which would have been decay. Okay, so that's our exponential growth. So just a quick question to see the power of exponential growth. It's at the bottom of this page. It says, suppose you're given a choice between two gifts. The first is $10 million in cash. The second is an account that starts with $2, but then doubles each day for exactly 24 days. Which would you take? Now, of course, the $10 million in cash does seem quite enticing, but if you were to take, say, this function, which is literally 2 to the power of 24. On the first day, 2 to the 1, you get $2. And on the second day, 2 to the 2, you get double that. And then 2 to the 3, double that, and 2 to the 4, double that. So if you were to plug in 2 to the 24, how much money would you have after 24 days? It ends up being $16,777,216, which is a fair bit more. I mean, if you kept going for, like, say a month, say 31 days, my goodness, that would be an enormous amount. You can plug it into your calculator if you wanted to figure it out. But exponential growth is quite powerful. So let's look at an example of this. So I'm looking at the back now. It's not a long lesson. So here we have a biologist grows a colony of bacteria in a petri dish and finds that after 1 day the quantity has increased by 50%. After 2 days it's increased by another 50%, and so on and so on and so on. The biologist is uncertain as to the exact initial number of bacteria. We're going to determine an algebraic formula that can be used to describe the quantity after 10 days. And then after n number of days, so however number of days you want to plug into the formula, we'll just say n. Alright, so in this case, what we do is we let P naught, right? P will let stand for population of bacteria, and naught is the symbol. It looks like a 0, but it's pronounced naught. Naught is the symbol to represent an initial amount. So that's our initial population of bacteria. Then after 1 day, it increases by 50%. So how could I write this? So the total number, let's say P after 1 day, we have what we started off with plus 50% of that, say 50% of P naught. Now first, just to talk a little bit about percentages, try it on your calculator. Type in 50 and then percent. What number do you get? You actually get 0.5. Because percentage is really a number between 0 and 1. 1 is 100%, 0 is 0%, 0.5 is 50%. Okay, so that's what we're going to look at. So 50%, if you were to type 50% on your calculator, you really just get 0.5. And that kind of makes sense. Look at it this way. Let's say this is 10. Well, this is 0.5 times 10. Well, 0.5 is the same as a half. So a half of 10 is 5. 10 plus 5 is 15. Right? That makes sense in what we're trying to look at, which says the number of bacteria increased by 50%. Right? You get half of what you had the previous day. An additional half of what you had the previous day. Right? So that works. So I'm going to write your handout keeps using percent signs all the way through it until the end. I'm just going to start just like this. I think it makes it look a little less confusing if we just leave out all the percentage signs, right? Because now we can see we can factor that, right? We have 2 p naughts there, so I can write this as p naught of 1, because it's 1 plus 0.5. Okay? Okay. Now let's look at, say, what would P2 be? Well, P2 would be what you had the day before, P1, plus 50% of that. Okay, so we're going to write 50% of P1, but instead of percent, we're going to write 0.5 P1. Sorry. P1. Okay, and remember when I write P1, I'm writing this function after 1 day. Okay, this function after 2 days. It's not P times 2, it's P where at 2 days. Right? So in this case, again, I can factor. I can have P1 all times by 1 plus 0.5. Kind of developing a pattern here, 1 plus 0.5, 1 plus 0.5. If I were to take P1, which I know, P1 equals this, and let's just take that and substitute it in for P1, what I get is that P2 is P naught times 1 plus 0.5 times this one, 1 plus 0.5. Okay, but these are the exact, these brackets are identical. It's like, well, what's x times x? X times x is x squared. So 1 plus 0.5 times 1 plus 0.5, I can just write as 1 plus 0.5 squared. And I can follow along the same pattern. Right? And I can say, well, P3 is going to be our initial amount times 1 plus 0.5 to the power of 3. I can keep going and say, okay, P after the population of bacteria after 10 days is what our initial amount was, plus 1 plus 0.5 to the power of 10. And if you want to know after n number of days, pick any value of n, you can probably see where this pattern is going at. P after n days is just our initial amount times 1 plus 0.5 after n number of days. Okay, so I'm just going to keep that original equation up there. I'm going to erase the rest. So that's our equation. What does this equation actually mean? Well, p to the n, that represents the final amount of bacteria, or whatever it is you're counting really, that's growing exponentially. The final amount of, in this case, bacteria after n number of days. So n is the number of periods in which that bacteria culture increases by 50%. In this case, the number of days. Okay, P naught is our initial amount, in this case, initial amount of bacteria. Okay? And again, n is the number of days. So what's this 0.5? Well, in this question, if we read the question, it said increases by 50%. So that's how much it increases. It's the rate at which it increases. So I can write an equation for any exponential growth to be some amount after a certain period n equals the initial amount multiplied by 1 plus the rate at which it increases to the power of that number of growth periods or cycles. Okay? So this is our equation for exponential growth, and you're going to see in chapter 8, we're going to see an equation that's identical to this, except we're going to call these variables something different, which is going to relate to financing, but it's going to be the identical equation. So let's finish with just an example at the bottom. It says, the population in a small town is predicted to grow at a rate of 8% per year. So that R is our 8%. That's our rate, 8%. Okay, but we're not going to write it as percent. We're not going to write a percentage sign. So as a number, 0.08. Okay, that says currently there are 25,234 people. So that's our initial amounts. That's P naught. P naught is, I lost it, 25,234 people. Right? And this is the terminal formula to calculate the population in 20 years. Well, we already have that formula. Now 20 years, that would be our cycle. So n equals 20. So we can actually calculate that. So P, the population after 20 years, is our initial amount, right? P naught, which is 25,234, multiplied by 1 plus our rate, R, 0.08, all to the power of how many cycles we have? 20. And practice plugging that in on your calculator. If you're having trouble, do it a step at a time. Do the bracket, take it to the exponent, figure out what that is, and then multiply. Okay? If you can do it all at once, great. But if you can't, split it up. But you should get 117,614. And I rounded down to 614. All right, so that's going to be our last lesson for this unit. Tomorrow I will post the Google Form quiz for Chapter 7. Okay, and make sure you go print out Chapter 8 if you can.